Okay, let's begin. We're now in section 9.2. We've already talked about the basics of significance testing, and now we're going to talk about doing it specifically with proportions. So like I said, we've already done the basics in section 9.1, did that while I was still in the country, and now we're going to talk about proportions, and later on we'll talk about how to do it with means. So here's our goals for this section. This includes 2 days worth of material. But to check the conditions for carrying out a test about a population proportion, as you'll see, it's the same three as before: random, normal, and independent. The difference is just that, you'll see. Small difference. Also, we'll need to know how to conduct a significance test about a population proportion and know how to construct a confidence interval to draw a conclusion for a two-sided test about a population proportion. Okay, now confidence intervals and significant tests are based on the sampling distributions of statistics. That is, both use probability to say what would happen if we apply the inference method many, many times. We already went over section 9.1, and that gave us kind of the basic reasoning behind significance tests, including the idea of a p-value. Now in this section, we're going to focus on doing it with a population proportion. We're going to look at both one-sided tests and two-sided tests. And once we get to the two-sided tests, we'll see how confidence intervals are actually related to two-sided tests. Alright, carrying out a significance test. Sorry, I'm tripping over my tongue here. Just so you know, there will be times I know you need to be writing down, and I'm going to try to pause or let you know to pause, but I think it'd be good for someone to be up at the projector so they can hit pause whenever you guys need some time to work out a problem or just to write things down before I move on to the next slide, because it's a little hard for me to have any idea how long I should wait. So please have someone ready to pause whenever that happens. So we talked before about a basketball player who claimed to be an 80% free throw shooter. In an SRS of 50 free throws, he made 32. So his sample proportion, his p-hat of made shots, 32 out of 50, is equal to 0.64, is much lower than what he claimed. But the question is, does it provide convincing evidence against his claim? Again, it's possible he is an 80% free throw shooter, and it's just kind of bad luck that this time he only got 0.64, because there is some sampling variability when we're doing that. But it's also possible this is convincing evidence, enough evidence to say we're pretty sure you're lying about being an 80% free throw shooter. So we're going to find out by performing a significance test. So our null hypothesis is that p is equal to 0.80. Our alternative hypothesis is that p is less than 0.80, and we choose that because we suspect, based on the sample proportion, that he's actually has a smaller percentage of making free throws than he claims. And please remember, we do need to define what p is. So we're saying where p equals the actual proportion of free throws the shooter makes in the long run. So we got to check our conditions. Same conditions we talked about before: random, normal, independent. So the random, we can see they said it was an SRS of 50 throws, so we're good there. Normal, assuming the null hypothesis is true, p is equal to 0.8. So then we do np to find the number of successes, which would be 40, and n times 1 minus b, number of failures, which is 10. Since both are 10 or bigger, the normal condition is met. And independent. In our simulation, the outcome of each shot is determined by a random number generator because we were using a simulation, so individual observations are independent. We don't have to worry about the 10% rule here because we're using a simulation, no sampling without replacement or anything like that. So the random, normal, and independent is the same as before, but there is a difference. With confidence intervals, we used p-hat when we were looking at the normal probability. We were doing n times p-hat. But with significance tests, we use p-naught. That's the p assumed in the null hypothesis. So it was p hat that we used when we were dealing with confidence intervals. It's p naught, the p from the null hypothesis, you call it the null p maybe, that we're going to use for np and n times 1 minus b. So that's really the only difference as far as the conditions we need to check. If the null hypothesis is true, then the player's sample proportion of made free throws in an SRS of 50 shots would vary according to an approximately normal sampling distribution with a mean of 0.80 and a standard deviation using the normal proportion sample standard deviation of 0.0566. So we would expect a standard deviation of about 5.6%. So here you see the sampling distribution of p hat if p equals 0.8. And here's what we need to calculate: the test statistic and the p-value. Now, a significance test uses the sample data to measure the strength of evidence against the null hypothesis. So these are some things we have to apply to most of our tests. The test compares a statistic calculated from sample data with the value of the parameter stated by the null hypothesis. So what you got to think about it is if someone's making a claim and you're testing that claim against some sample or some experiment that we run to get data. Values of the statistic far from the null parameter value in the direction specified by the alternative hypothesis give evidence against the null hypothesis. Okay, so here's what they're pointing out. Like right now when we're looking at the number or the proportion of free throws this guy is making, he says it's 0.8. If he did a sample and it was 0.95, well, that's pretty far from 0.8, but it's not in the direction we were suspecting or testing. So even though 0.95 is a long way away from 0.80, that actually wouldn't give any evidence against the null hypothesis, because what we're testing is the null hypothesis against the idea that the true proportion is less than that. So the direction specified by the alternative hypothesis matters. It's only going to be things in our example here where the sample proportion is less than the null hypothesis that we're going to be adding evidence against the null hypothesis. So make sure you do pay attention to what direction we're going. So here's the definition. A test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis were true in standardized units. So this is similar to finding the z-score. So to find that, we do the test statistic equals the statistic, so the sample proportion in this case is our statistic, minus the parameter, that's in this one the proportion of the null hypothesis, all divided by the standard deviation of the statistic. The test statistic says how far the sample result is from the null parameter value in what direction on a standardized scale. You can use the test statistic to find the p-value of the test. In our free throw shooter example, the sample proportion 0.64 is pretty far below the hypothesized value of 0.8 from the null hypothesis. So you can see here how we've standardized it. Our statistic is our sample proportion, that's 0.64. Our parameter is what the null hypothesis claims the true proportion is, which is 0.8. And then we found from the sample proportion standard deviation formula previously the standard deviation of 0.0566. So we compute that and we get a z-score of negative 2.83. So remember, that means the sample, what he did in this test, is 2.83 standard deviations below the claimed proportion. So you can see right there on the graph that it is pretty far away. The top graph is just showing it in terms of proportion. The bottom graph is showing it in terms of standardized scores. Now the shaded area under the curve shows the p-value. That shows the area on the standard normal curve which displays the distribution of the z-test statistic. So you can use table A and check out the z, and just look at the value for that z-score of negative 2.83. Or you can use normal CDF in your calculator, and you'll find the p-value is 0.0023. So that means the probability of this basketball shooter, if it's true that he has actually a free throw proportion of 0.8, the probability of him having 0.64 as his proportion in 50 shots is about 0.23%. So less than a quarter of 1% likelihood. So you can see the way they say it. If the null hypothesis is true and the player does make 80% of his free throws in the long run, there's only about a 2 in 1,000 chance that the player would make as few as 32 of 50 shots. So I'd say that's pretty strong evidence against his claim. Again, doesn't guarantee it. There is a chance, though it's a very, very small chance that he's telling the truth. So this is pretty convincing evidence against his claim. So let's try this example. In an SRS of 100 voters, 56 favored Jack Sparrow walking the plank. So let's calculate the test statistic. Because the hypothesized value would be 0.5, just going with the idea of either he is or he isn't, a 50-50 shot, the standardized test statistic would be 0.56, which is the SRS. And since we really didn't know anything about the proportion, 0.5 is kind of a go-to if no information is given. That's what we can test it against, because we're really curious, do people want him to walk the plank or not? So 0.5 would be kind of the standard bearer, because if the majority do, it's above 0.5. If the majority don't, it's below 0.5. Since we're curious if people would want him to walk the plank or not, that's why we're using 0.5 as our null hypothesis P. So you can see that the test statistic would be 1.2. That tells us that if it's truly a 50-50 that people want Jack Sparrow to walk the plank, then 0.56 from an SRS would be 1.2 standard deviations above the 0.5. Then we find and interpret the p-value. You can use table A, or you can use norm CDF 1.2 up to 100. We often use the 1E99 instead of 100, but you'll get pretty much the same answer either way as long as you put in a big number. We get 0.1151. So if exactly 50% of all voters support Jack Sparrow walking the plank, there is about an 11.5% chance that 56% or more voters would support Jack Sparrow walking the plank in a random sample of size 100. So compared to our previous example, there's a little more evidence that this could still be possible. It may be that exactly 50% of all voters support Jack Sparrow, because there's a greater than 10% chance that 56% in an SRS like this would support him walking the plank. So there's less evidence against the 50% claim than there was against the free throw guy's claim. So bigger p-value means a greater probability of the null hypothesis being true based on the sample data. Again, feel free to pause if you ever need to be able to write more stuff down. And sorry if the 50% thing seems confusing. I didn't put a whole lot on the slide just trying to save space, but it would specify in almost every problem what our claim is. So you just need to make sure you pull that P from the null hypothesis. So here we go. We're doing a one sample z-test for a proportion. And your favorite, the 4-step process. So with state, what hypotheses you want to test and at what significance level. Define any parameters you use. So make sure you define P. With plan, you'll choose the appropriate inference method, which right now is the one sample z-test. Then you'll check the conditions. In the do, if the conditions are met, then you'll perform the calculations. You'll actually also, one thing you didn't write here, I've got this on a later slide, but you'll need to show your p hat, compute the test statistic, which for right now is going to be a z-score, and then find the p-value. Then you'll interpret your results in the context of the problem. So make sure when you are interpreting, you are actually talking about this problem and not just speaking generally. You don't just want to say something like, therefore we reject the null hypothesis. You want to say we reject and then say what it is. So on a previous example, we might say, we reject the basketball player's claim that he is an 80% free throw shooter. So make sure you're putting these in context and talking about that specific problem and its circumstances. So when conditions are met, R and I, random, normal, and independent, the sampling distribution of p hat is approximately normal with a mean of p and a standard deviation of things we've worked with before. Square root of p times 1 minus p all over n. Okay, and that's just a reminder of what I talked about earlier. We are using p naught, or the p from the null hypothesis, in our calculations. So we are assuming the null hypothesis is correct. One thing we may have talked about in the first section is that you can almost think about this like when people are in court. We are assuming when people, or at least what we're supposed to do in our country, is we are supposed to assume innocence until they are proven guilty. So the default when someone is being brought before a court is to assume they are innocent and wait to see evidence otherwise. And we do the same idea here in this significance testing. We assume the null hypothesis is true, but then we look for evidence that would say otherwise. The z-statistic has approximately the standard normal distribution when the null hypothesis is true. P-values therefore come from the standard normal distribution. So here's a summary. We'll choose an SRS of size n from a large population that contains an unknown proportion p of successes. To test the hypothesis that p is equal to p naught, compute the z-statistic. We've been using that throughout this. And then find the p-value by calculating the probability of getting a z-statistic this large or larger in the direction specified by the alternative hypothesis. So you can see in those pictures, the greater than makes sense. You look for the area greater than that z-score. Less than, you look for it less than that z-score. And when the alternative hypothesis is that p does not equal p naught, we look at it from both directions. So notice, we use the absolute value of z. It doesn't matter what side z is on, we use both signs of it basically. So if we get a z of -2, we look at the area to the left of -2 and to the right of +2 and add those together. Or, since a normal distribution is symmetric, you can just find one of those numbers and then double it to account for the other side. Okay, don't forget, use this test on expected number of successes and failures based on the null hypothesis. E naught and n times 1 minus p naught are both at least 10, and the population is at label if we're sampling without replacement. So just a reminder there about our conditions. Okay, here I've laid out for you the required pieces of the 4-step process. Since we're about to do an example, I'm not going to read through all this right now. We will be doing this, though, in just a couple slides in an example. But this really helps you see what needs to be said, what do we need to do when we're doing a 4-step process with significance tests for proportions. This is on 2 slides. So we've got the state, the plan, the do. And then there's more do. And I have it color-coded here just to make sure you see what you're going to say here depends on what direction your alternative hypothesis is saying. The ones in blue are if our null hypothesis is that it's greater than the null hypothesis, p, and then the red is if it's less than, and then the green is if it's not equal to. And conclude, notice there are 2 options there. If our p-value is greater than our chosen significance level, we fail to reject the null hypothesis. or if it's less than the chosen significance level, we do reject the null hypothesis. So most likely, in the two examples we looked at today, with the basketball with such a low p-value, we would almost certainly reject the null hypothesis at almost any chosen significance level. Whereas the second one we looked at, which where the p-value was more like 11, I think about Jack Sparrow walking the plank, that'd be more likely that we would fail to reject because it's likely bigger than the significance level we'd pick, which are more commonly things like 0.05 or maybe even 0.10, but it's still bigger than that one. Okay, one important note. When we're in our conclusion, it would be incorrect to say we have evidence that this is true or we have evidence that this is false, because that would imply we know for certain, which we don't. So what's better to say is we have convincing evidence to reject this, or convincing evidence to fail to reject this. And you can say convincing or sufficient evidence. But the main thing I'm trying to drive home here is our significance testing is not telling us for certain this is true or for certain this is false. What it's saying is there's a lot of evidence that either it's true or it's false. So make sure you use words like convincing evidence or sufficient evidence to help show that we are just talking about the amount of evidence for or against something, not saying with absolute certainty what it is. So here's our example with potatoes. So a potato chip producer has just received a truckload of potatoes from its main supplier. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. So let's carry out a significance test at the alpha equals 0.10 significance level. And then, what should the producer conclude based on the results of the test? So here's an example where I'd like someone to be pausing as we go, because I'm going to kind of roll through, but I really do want you guys to try it on your own ahead of time, if there's time in class. I'm realizing this video is going pretty long, so if you need to just roll through and try on your own later with homework, that's okay too. But if there's time, pause to give you time to work through it on your own, at least one piece at a time. So 4 steps, here we go. State, we want to perform a test at the alpha equals 0.10 significance level of the null hypothesis that p is equal to 0.08 with the alternative hypothesis that p is greater than 0.08, because the producer wants to determine if more than 8% of the potatoes have blemishes. So that's why we're choosing greater than. P is the actual proportion of potatoes in this shipment with blemishes. So do not forget to define your P in the context of the problem. We have now stated, time to plan. If the conditions are met, we should do a one sample z-test for the population proportion P. Random. We were told he took a random sample. We're good. Normal. Assuming the null hypothesis is true that P is 0.08, the expected numbers of blemished and unblemished potatoes are 40 blemished and 460 unblemished. Those are both 10 or bigger, so we should be fine using normal calculations. Independent. We are sampling without replacement, so in this case we need to check the 10% condition. But it does seem reasonable that in a truckload of potatoes there's at least 5,000, so we show, don't forget to show this, we do 10 times 500 equals 5,000, and we think it's reasonable to assume there are at least 5,000 potatoes in the shipment. But show that 10 times 500 equals 5,000 part in that. Time for do. Got 3 pieces really. First, we show the sample statistic, the sample proportion of blemished potatoes. In this case, it's 47 over 500 equals 0.094. And it is good to show that fraction to make sure they know exactly where you got it. Where you got the 0.094, I mean. Then we need the test statistic. p hat minus p naught over the square root that gives us the standard deviation. So we get a z-score of 1.15. So our sample is 1.15 standard deviations above the mean that would be expected if the null hypothesis is true. So then you can use table A or normal CDF and find a p-value of 0.1251. In other words, there's a 12.5% likelihood of us getting a sample that far away or farther from the true mean if the null hypothesis is true. So we did our 3 steps for do, showed our sample statistic, our test statistic, and our p-value. So now we can conclude. Since our p-value is greater than the chosen significance level of alpha equals 0.10, we fail to reject the null. There is not sufficient evidence to conclude that the shipment contains more than 8% blemished potatoes. The producer will use this truckload of potatoes to make potato chips. And, good news, we can calculate the p-value for this in our calculators using the one-prop z-test. Okay, this AP exam tip you can read on your own on your paper, but it's similar to what we said before. Showing work helps because if you ever make a mistake on the calculator and you only have the answer, you'll get no credit. But if you've got correct work and a wrong final answer, you can get partial credit even on the AP test. But let me back up so we can see these numbers. And then we'll do the one sample or one proportion. Yeah, we'll see. So we go to stat, go over to tests, and we are doing the one prop z-test. Number 5, one prop z-test. Okay, our p naught for this was 0.08. X is how many successes, that would be how many blemished ones in this case, that was 47 out of 500. And our alternative hypothesis was that it's greater than 0.08. So we'll do that, and you can just go to calculate. Oh, I forgot to hit enter. Make sure once you select it, you hit enter, so it highlights that one. So that's all you have to plug in, and we get this. So you can see z-score 1.15 matches, and our p-value, that's one that just says p, is 0.124. Notice that is slightly different from what we got. That is okay on my test and quizzes, and that is okay on the AP test. They know the values you get from table A versus the values you get in the calculator can be slightly different, but 12.42% and 12.51%, it's not really any difference that matters. Alright, getting close. I know it's been a long one. Bear with me. Let's try one more example. On shows like American Idol, contestants often wonder if there's an advantage to performing last. To investigate this, a random sample of 600 American Idol fans is selected, and they are shown the audition tapes of 12 never-before-seen contestants. For each fan, the order of the 12 videos is randomly determined. That's good. Thus, if the order of performance doesn't matter, we would expect approximately 1/12 of the fans to prefer the last contestant they view. In this study, 59 of the 600 fans prefer the last contestant they viewed. So that's almost 1 in 10. Does this data provide enough convincing evidence that there's an advantage to going last? For the sake of time, I'm just going to show you these and walk through them. So here's where we state we want to perform the test at 0.05 significance level. Our null hypothesis is that it's 1/12, but we suspect people like the last one they see, so we suspect that p is greater than 1/12, where p is the true proportion of American Idol fans who prefer the last performance they see. Remember, if I'm going too fast, you have access to this through Google Classroom, and you can pause this and fill in anything you need. So plan if the conditions are met, which, hey, all of them are. Surprise, surprise. So then we go to the do. We find our p hat. So I think there should be a hat there above that p. 59 over 600 equals 0.098. So our test statistic is 1.33. we can then use Table A or normal CDF to get a p-value of 0.0918. Since the p-value is greater than our alpha, 0.05, we fail to reject the null hypothesis. Basically, there's an over 9% possibility of it going this way, even if the true proportion is 1/12. So we say that's enough evidence, or not enough evidence to go against the null hypothesis. So there is not convincing evidence to conclude that there's an advantage to this. All right. I'm going to run it in here just so you're sure you know how to do it in the calculator. So we go to Stat, we go to Tests, we go to the one prop z test, number 5. And this time our p naught is about, I'll just type in 1/12. It is about 0.083. Let's see. Our x is 59. Our sample size is 600. And we think greater than, so we're good there. And then we calculate. Oh, I did something wrong. Let's see if I can figure it out. It may be, I can't remember. Maybe the calculator isn't like, no, I changed my fraction. Oh, it only did 6 instead of 600. There we go. It's hard to have 59 successes in a sample size of 6. Okay, so I just need to change the sample size to 600. And I just hit the wrong one. We want greater than. Now we should have it. Okay, good. So our p is the 0.09186. So almost exactly matches what I have there. And you can see it is greater than the null hypothesis, or the significance level of 0.05. But this is an example where the significance level chosen does matter. Because if we had chosen a 10% significance level, we would have rejected the null, because that's less than 10%. But with a 5% rejection, or significance level, we'd have to reject the null. So that really does matter. And that's part of why it's important to choose those things before you take the test. All right, 2 quick examples. Describe a type 1 error in the setting of this American Idol problem. So remember, a type 1 error is when we reject a true null hypothesis. So that would be concluding the probability of winning when you are the last contestant is greater than 1/12, meaning we reject the null, when in fact the probability is 1/12. So type 1 is when we reject a true null hypothesis. Type 2 is when we fail to reject a false hypothesis. So in this problem, you would be saying that we do not have enough evidence to conclude that the probability of winning when you are the last contestant is greater than 1/12, when in fact, the true probability is greater than 1/12. Okay, last one. I know this has been a long video. So the test has a power of 0.78 to detect that p is equal to 1/10. Explain what this means. Well, let's do that. If p equals 1/10, if the true proportion is 1/10, the probability of correctly rejecting this null hypothesis is 0.78. So that is the power to correctly reject the null hypothesis. When we talk about power, that's what it is. It's the power to correctly reject the null hypothesis given that data. And in what ways could we increase the power of this test? Well, it turns out we can increase the power by increasing the sample size or by increasing the significance level. So try to keep in mind how those things relate: sample size, power, and significance level. So there's your homework for this section. Don't worry, part 2 is not as long as this one. Good luck.